Today we're going to talk about scientific and engineering notation. And the first question you might ask is why? Why do we use scientific and engineering notation? Well, these were developed to easily represent very, very large numbers or really, really small numbers. To illustrate, let's look at a couple examples. The Andromeda Galaxy, which is the closest galaxy to our Milky Way, has at least 200 billion stars. On the other hand, during the radioactive decay of plutonium-239, it emits an alpha particle that weighs the amount that's shown here on the screen. I don't even know how to say that number. As you can imagine, it would get rather tedious to write out this really small number or the very large number on the previous slide repeatedly, and it's quite easy to leave off or add an extra zero. Now that might not seem important, but to put it in perspective, if you owed the bank $1,000, you certainly wouldn't want them to add an extra zero and ask you to pay them $10,000. So let's look at one example. That 200 billion stars can be written this way. It can also be written as 2 times 100 billion, but it's this 100 billion that causes the problem. But in fact, 100 billion is just a multiple of 10. In fact, it can be written as 10 times itself 11 times. A more convenient way to represent that is to write 10 to the 11th power, where the 11 is the exponent that represents how many times 10 gets multiplied by itself. So 10 to the 1 is just 10. 10 to the power of 2, you multiply 10 by itself 2 times and you get 100. 10 to the 3, you get 1,000, and so on. So if we take 200 billion, we can represent that as 2 times 10 to the 11th power, or 10 multiplied by itself 11 times. And this is 200 billion written in scientific notation. Any number can be represented in scientific notation. To be in scientific notation, you need to have just one digit in front of the decimal point. Any number of digits can follow that, and then it's multiplied by a factor of 10, where n is the exponent that represents the number of times that 10 is multiplied by itself, or the magnitude of the number. So, for example, if we have 12,300, that can be represented in scientific notation as 1.23 times 10 to the 4. And the exponent 4 represents how many places we've moved the decimal point. So it started here, and we moved it 1, 2, 3, 4 places. Now, the positive exponent represents a relatively large number, 10 multiplied by itself 4 times or however many times. But what do you do if we have a really small number, like the weight of that alpha particle? So to represent a really small number in scientific notation, I'm going to need a negative exponent, which indicates a negative power of 10, or a fraction with 1 in the numerator and a power of 10 in the denominator. So remember, 10 to the 1 is 10, 10 to the 2 is 100, 10 to the 3 is 1,000. Well, if I take 10 to the negative 1, that's 1 over 10, or 10 to the negative 2 will be 1 over 100, and 10 to the negative 3 will be 1 over 1,000, and so on. So if I want to take this number here and put it in scientific notation, I need to figure out how many places to move the decimal. So the decimal starts here, and I'm going to move it 1, 2, 3, 4, 5, 6, 7, 8, 9, 12, 15, 18, 21, 24, 25, 26, 27 in order to have just one digit in front of the decimal. So it'll be 6.645 times 10 to the negative 27, which is the same thing as 6.645 times 1 over 10 to the 27. So this is the way to write this very small number in scientific notation. So let's take a look at a few examples. In this first one, to put this in scientific notation, we need to first determine where we want the decimal. Well, we want the decimal to be right behind the first digit, because we only want one digit in front of the decimal, so it's going to be 2.364 times 10 to some power. To determine what that exponent is, we have to figure out how many places we moved the decimal. So the decimal started out here, and we need to move it 1, 2, 3, 4, 5, 6, 7, 8 places to get it right behind the 2. So the exponent will be 8, and it's going to be positive. We've moved the decimal to the left, so we know it's positive, and this is a really big number, so it makes sense that we want to multiply 2.364 times some large number in order to get this. In the next one, first determine where you want the decimal. I want it right here, so I only have one digit in front of it. So 6.5 times 10 to what exponent? Well, here's where my decimal starts, so I'm going to move it 1, 2, 3, 4, 5, 6, 7 places. In this case, I am moving the decimal to the right, so the exponent is going to be negative, which makes sense because this is a small number, so I would want to multiply 6.5 by some very small number, so a fraction here. Again, this is how it's written in scientific notation, but to get you to see that it's a really small number. And the last example, where do we want the decimal? Right here after the 3, so it's going to be 3.46 times 10. And how many places do we move the decimal? We starts here, we move it 1, 2, 3, 4 places. We're moving the decimal to the right. It's going to be negative, which makes sense because this is a really small number. So engineers are quirky, so we've developed our own notation. But really the reason we've done this is because the engineering notation lines up with the prefixes in the SI units, which we'll talk about in the near future, and it also makes the mathematical calculations easier. So the key to the engineering notation is that the exponent for the power of 10 has to be a multiple of 3. So a multiple of 3 can be 3, 6, 9. And in order to do that, the number in front of the decimal can be anywhere between 1 and 999 inclusive to yield a power of 10 that's a multiple of 3. So if we look at this, 12,300 in scientific notation. In scientific notation, the key is that you want one digit in front of the decimal place. So we would want the decimal here, 1.23, and we'd have to move the decimal 1, 2, 3, 4 places, so the exponent would be 4. In engineering notation, we want this exponent to be a multiple of 3. So in this case, we would move the decimal 1, 2, 3 spots, and that makes a 12 in front of the decimal. So it's 12.3 times 10 to the 3. If we moved it another 3, 1, 2, 3, you would have something that's less than 1. So it's not between 1 and 999. So you would not say 0.0123 times 10 to the 6. That's not engineering notation. You want this number in front of the decimal to be somewhere between 1 and 999 inclusive. So let's take a look at a few examples. What I'd like you to do is pause the video and write on a sheet of paper each of these 4 numbers in both scientific notation and engineering notation. So pause the video and restart it once you have done that. Here are the answers to check your work. Remember, the key to scientific notation is you want one digit in front of the decimal place, and you move your decimal in as many places as you need in order to accomplish that. In engineering notation, you want your exponent to be a multiple of 3, and you move your decimal as many places as you need to maintain the exponent a multiple of 3 and to have the number in front of the decimal between 1 and 999 inclusive. If you had trouble with these 4, then please go back and review this video. Otherwise, I'd like you to go to the practice quiz on Blackboard on scientific and engineering notation and do that. Now, I said at the beginning of the video that we use scientific or engineering notation to more easily represent really large or really small numbers, which is true. But another benefit of using the scientific or engineering notation is that it reduces the ambiguity when it comes to significant figures. So for example, if we have 2,303, we know that this number has 4 significant digits. But if we have 23 million right here, we don't know whether this has 2 significant digits, or maybe it was measured and really has 5 significant digits. We don't really know. Maybe it has 6. So in order to eliminate that ambiguity, if we have it in engineering or scientific notation, let's take engineering notation. If I have 23 times 10 to the 6, then I know that there's 2 significant digits. If there were 3 significant digits, for example, then I would write it as 23.0 times 10 to the 6. And that is telling you that this 0 then is significant. Okay, similarly, I could write 23.00 times 10 to the 6, and that's telling you that this now has 4 significant digits. So using the engineering notation helps also with reducing the ambiguity on significant figures.